So let us try to derive the geodesic equation in general relativity, which is fairly simple as you'll see. Now you might be already familiar that the line element in relativity is given by some ds square equals g mu nu, dx mu and dx nu, right? Where g mu nu is your metric tensor, and if I want, I can write this like this: g mu nu dx mu upon dt times dx nu upon dt times dt square. This does not change the equation, right? And the dt that I'm using over here is the proper time. It's not the usual time, it's the proper time that we use in special relativity. Now ds becomes square root of g mu nu times dx mu upon dt times dx mu upon dt and dt outside the square root. Notice this thing over here. These things are just the velocities, right? So ds can be written as g mu nu x dot nu times dt, and all this thing under the square root. And what happens if we try to integrate both the sides, right? We integrate both the sides and then we take the variation and equate it to 0. Well, this is just the Hamilton's principle. So if this is the Hamilton's principle, then this thing over here must be the Lagrangian, right? So we have our Lagrangian. Our Lagrangian is given by square root of g mu nu x dot mu, right? All we got to do is write down the Euler-Lagrange equation, which is given by this, and then we have to calculate the individual derivatives. So first let's calculate this derivative. Let us calculate this derivative. This is just going to be the derivative with respect to x alpha of the Lagrangian that we have, g mu nu x dot mu. This is going to give us 1 upon 2 g mu nu x dot mu times x dot mu and the derivative of the metric tensor, right? This thing can be simplified and written as 1 upon 2 g mu nu x dot mu times x dot mu d alpha g mu. Now there is one thing to note over here. Look at this quantity. If I take this dt on the other side of the equation just becomes ds upon dt is equal to g mu nu. It becomes g mu nu times x dot mu, right? Notice this quantity. Well, this is just a constant, right? This is just a constant because ds is a line element and it is invariant, and dt is the proper time, which is also invariant. So this thing is going to be a constant and it is going to be equal to the speed of light, right? This is just c. So I should write it down somewhere over here that ds upon dt is just c, which is equal to g mu nu x dot mu. So now this equation gets simplified, right? It is just 1 by 2c x dot mu d alpha of g mu nu, and this is dl upon dx alpha. Now in a very similar way, let us try to get this derivative, right? This is going to be a derivative with respect to x dot alpha of our Lagrangian, which is g mu nu x dot mu. At first it would be a simple derivative which would be equal to 1 upon 2 times square root of g mu nu x dot mu, and for the chain rule we'll have to use the product rule inside this, right? So we'll write g mu nu, will leave the first term x mu and we'll take the derivative with respect to the second term, which is x dot nu. Then we'll leave the metric tensor and the second term and we'll take the derivative of the first term, which is x dot mu. Let us simplify this equation a bit further. Now let us talk about this derivative, right? It says dx dot nu by dx dot alpha. Notice that this derivative is going to be 1 if nu is equal to alpha, and it is going to be 0 if nu is not equal to alpha. And this is precisely the definition of the Kronecker delta, right? Now we can simplify this equation as 1 upon 2c g mu nu x dot mu with the Kronecker delta nu and alpha plus g mu nu x dot mu and the Kronecker delta with mu and alpha this time. Now there's one catch. Look, uh, this thing over here is going to be 1 if nu is equal to alpha. So all we gotta do is replace all the nu's with the alpha. We have a nu over here, right? So this thing becomes 1 upon 2c g alpha mu x dot mu plus g alpha nu x dot nu, right? Because here also we have mu and alpha, and this thing is going to be 1 if mu is equal to alpha. So all you got to do is replace all the mu with alphas, right? So we have this thing over here. Now as you can see that in this case nu is the repeated index, right? We have a nu over here and then we have a nu over here, and if something is a repeated index, that means it is being summed over, and it is a dummy index also. So we can replace this with anything, right? Here also we have a mu and mu, so we can just replace it with any other thing. It's just a dummy index, so I can replace it with nu. So I will get a 1 upon 2c g alpha nu x dot nu plus g alpha nu x dot nu. This just becomes 1 upon 2c times 2 times g alpha nu x dot nu. The 2's get cancelled and we are left with g alpha nu x dot nu and definitely 1 upon c, right? And this was our dl upon dx dot alpha. So we have also calculated this derivative. Now we have to calculate the time derivative of this thing, right? We have to calculate this d upon dt of dl upon dx dot alpha, which is going to be d upon dt of g alpha nu x dot nu. We'll have to use the product rule again, and by the product rule we are going to get let's leave the x dot nu for the first time, and we'll have d upon dt of g alpha nu. This time let's leave the metric tensor alone, and we'll have the time derivative of x double dot nu. Well, this thing is simple. This is just going to be x double dot nu. It's going to be the acceleration, right? So I can replace this thing and I can write it as x double dot nu. Now what about this thing? This thing looks complicated, but then we can assume that the metric tensor is the function of some other variable beta, and then we can use the chain rule to write it in somewhat this fashion. It's going to be d upon dx beta of g alpha nu, and then we'll take the derivative of x beta with respect to time, and we are left with this. On simplifying this thing, this becomes 1 upon c of x dot nu d beta g alpha nu times x dot beta plus g alpha nu x double dot nu. So we have calculated the time derivative also, and therefore we can write that d upon dt of dl upon dx dot alpha is this thing, right? Now let us put our equations to our findings to the Euler-Lagrange equation. So the Euler-Lagrange equation would now become 1 upon c x dot nu x dot beta d beta g alpha nu plus g alpha nu x double dot nu, and the other equation was x dot nu times x dot nu and d alpha g mu nu upon 2c. The c's get cancelled out. C's gets cancelled out, so I can just remove this from here, and we are left with this thing. Now we have to manipulate things a bit. Uh, we have to manipulate this term specially. Why do we need this manipulation? Well, the primary purpose of this manipulation would be to put things in terms of affine connection, or the Christoffel symbols, right? So, what are Christoffel symbols? The Christoffel symbol of the first kind, uh, the Christoffel symbol of the first kind is defines something like this. It's written as, say, beta, nu, and alpha, and it is defined as 1/2 times d beta g nu alpha plus d nu g alpha beta minus d alpha g beta nu. This is how the Christoffel symbol of the first kind is defined, and we want to put things in this term only. That is why manipulation is required. So, how do we manipulate? Let's see. First, let us isolate the term that we want to manipulate. We want to manipulate d beta of g alpha nu x dot nu times x dot beta, and notice this thing can be written as d beta g alpha nu x dot beta plus d beta g alpha nu x dot beta, and the whole thing divided by 2, right? It's the same equation, so I can write this as, now notice that beta and nu, these are the two indices that are being summed over, right? So if something is summed over, it's again a dummy index and we can replace it, but here I will try to interchange them. How? Let's see. We have 1 by 2 d beta g alpha nu x dot beta. We'll leave the first term as it is, and now we will try to interchange beta with nu. So wherever you find a beta, you interchange it with alpha, and wherever you find a you interchange it with nu, and wherever you find a nu, you interchange it with beta. So we have a d beta over here. I can write this as a d nu g alpha, and now I have to write a g beta, and then we should write x dot beta and x dot nu. So you see, these two equations are essentially the same, but the form has changed, right? And this is going to help us a lot, as you'll see later on. So now with this sort of manipulation, we can let us first simplify this, right? I can write this as 1 by 2 d beta g alpha nu, and I can take these things common, and I will be left with d nu g alpha beta x dot nu and x dot beta, right? I have this thing. Now with this manipulation, let us see how can we write our Euler-Lagrange equation once again. We'll have to write 1 upon 2 of d beta g alpha nu plus d nu g alpha beta, everything outside as it is, and then we had a g alpha nu x double dot nu. So g alpha nu x double dot nu, and then with a minus sign we had 1 upon 2 x dot mu x dot nu d alpha g mu nu, and this was all equated to 0. Now notice we have half times something over here, and we have half times something over here, right? It would be great if we can take this equation inside, and then we can take the halves common, right? So how do we do that? We have a x dot nu in here and x dot beta in here, and we have a x dot nu and x dot mu. So all we gotta do is replace this mu with beta, right? So mu appears here and mu appears here. Let us try to replace that. We can write this as 1 upon 2 d beta g alpha nu plus d nu g alpha beta times x dot nu x dot beta plus g alpha nu x double dot nu minus 1 half times. Now this will become x dot beta and x dot nu d alpha g beta nu is equal to 0. Now we can take this equation over here, right? If we do that, we can take the half common and we will be left with d beta g alpha nu plus d nu g alpha beta, and our new equation which is just minus d alpha and g beta nu, and the things that we have taken common, that is x dot nu and x dot beta, and the other leftovers, which is g alpha nu x double dot nu is equal to 0. Now have a look at this. This will tell you why did we do the manipulation in the first place. Well, this whole term is just the affine connection. Look at this. This whole term is just the affine connection, right? So this can be written as the Christoffel symbol times x dot nu x dot beta plus g alpha nu x double dot nu is equal to 0. Now if we send this part of the equation on the other hand side, we'll get minus g alpha nu x double dot nu, and notice again that nu is the repeated index, and therefore we can replace it with something else. We can replace it with something like k, right? So this is the very general form of the equation. Now what do we do next? Well, how do you change the Christoffel symbol of the first kind to the Christoffel symbol of the second kind? Let us see if we have say some Christoffel symbol I, J and K, and we want to change it to the the Christoffel symbol of the second kind, which will have one index on the upper side. So we'll have some Mij. Well, you know that this sort of transformations can be brought about by the use of metric tensor, right? So if we have some metric tensor, say gmk over here with the upper index, so the k in this index is the is being summed over, so it's going to contract, and we will be left with just the m, right? And this would result in raising the index of the affine connection. So we can do this over here, right? We have a metric tensor over here, and if we bring the metric tensor to this side of the equation, nothing changes because the inverse of the metric tensor is similar to the metric tensor itself, right? This property holds with metric tensor. So we can write this equation as, say, g alpha k and Christoffel symbol with the index beta, nu and alpha, x dot nu x dot beta plus x double dot k is equal to 0. Now alpha is the repeated index and therefore is getting to be summed over, and we will be left with k. So this will change this to the Christoffel symbol of the second kind. This will be k beta nu and of course x dot nu and x dot beta plus x double dot k is equal to 0. And this is precisely your geodesic equation in general relativity.